and the title of the chapter is common mistakes and how to avoid them. So it is mostly reading stuff, but I will just highlight. So it lists about 22 common mistakes that people make, but this chapter also then presents how to avoid them. So I will just list those 5 or 10 points, right. So what we need is a systematic way, right, of how to go about this performance evaluation process. Those 6 or 6 steps that I showed, right, we will expand on a little bit more to have the specific list of steps that one should follow. Okay. So this will sound more or less like software engineering first part, because in software engineering what is the first thing that you do? The first thing that you do in software engineering project, right? So you should know what it is that you want to build. Likewise here, you should first define what it is that you want to build, right? And also the design goals of the system. Are you trying to design for high utilization or low response time, right? What is it? What is the system goal? So that should be clearly stated, because only based on that you will try to define your metrics and define your experiments and so on, right? So first is define the system, and state the goals of the system, right. So if you are in the banking industry and right, the bank decides that it wants to automate all this processing, right, we have more or less many systems now that do that. Let us say that they did not exist and the bank suddenly decides, let us try to give internet access to everybody, right. Okay, great. So you can do all your transactions via the net or via some phone and things like that. Then you have to decide, okay, that is the overall stated goal, but what is the main or stated system objective? Specifically, what do you want to do? Do you want to reduce the time that the user spends in the bank, or increase the time the user spends in front of the computer, right? Right now it is the other way around. We spend less time in the bank but more time in front of the computer, especially some banks, I won't name them, right? You sit there and keep waiting for the page to load. Why? Because somebody somewhere did not do the right performance evaluation, bottleneck analysis, didn't tune the parameters correctly. If they didn't have the right number of servers in the system, then your user delay gets to be much higher. So you should be very clear, I want to reduce the time that the user spends on a particular transaction. If you go to the bank, if it takes half an hour, right, in the olden days just to withdraw 500 rupees from the bank, now the goal is to make that much smaller than that. So if you go to the ATM, hopefully it is less than that, right, 10 minutes you can be done with the ATM transaction. So that is what we mean by state the goals of your system itself, because the goals tie to what performance objectives we have, right, and based on that everything else has to be defined. If you do not care about response time, you only care about processing large number of transactions per second or something like that, then you can define your metrics appropriately. If it is response time, that has to be one of the metrics that you measure, right. So that is the first step, is to design the overall goals and then list the services and the outcomes. This is also similar, I mean it is kind of generic to what we say, right. So this is the system high level definition and so particular services, right. So what is a particular service? If it is let us say RMI, right, RMI, RPC, RMI, you know the term, right. So either a remote procedure call or remote method invocation, that is the system that you want to define a new kind of RMI technique, right, or RPC technique. So what is the goal here? You can say, right, so the outcome, the service offered is a user will be able to invoke a process on a different machine and then get the response back, right. So therefore what is the service offered by the system, and the expected outcome is that you give a program, you give the necessary whatever, you give the code and the parameters, other system will simply run it and get you back the result. So that is the expected outcome. So these are also so these two fall more or less in your software engineering domain. Only thing is we also try to understand what the key performance metrics are, right. From a performance point of view, what is important, that is your customer has to come out and tell that this is more important to me than anything else. So once I know what the system does and what the various services are, right, then I start defining my metrics. Okay, so now we start defining some terms. So metric is a term which I find in thesis and reports and so on, which is very easily confused with parameters. People talk about parameters when they mean metrics and vice versa, right. So metric is something that is measured in a system, right. That is something that is a measurable quantity of a system. So delay, right, is a measurable metric. I send packets to the system and I measure the delay that each packet is experiencing, right. That is a metric of the system. So metric is, these are the measured quantities. Right. So for example delay, or you might say, right, throughput, how many transactions per second can a database server support, right. That is from the server point of view, that is what they report, right. If you look at your bus specifications in the system, it will tell you how many transactions per second or how many transfers per second is what they will give you your, right, GT per second and so on. So that is something that you can measure. You can define as many metrics as you want, but as a performance evaluation expert you are supposed to know what is more important and what will necessarily capture, right, the essence of these goals. So these metrics have to be tied to your goals and outcomes of the system, right. Otherwise you will end up measuring the wrong things and then you will not know how the system actually is behaving. Okay. Then you list the parameters. Okay. So parameter is something that will control the behavior of the system, that will have an impact on the system's performance. Okay. So this parameter is the variable, the independent variable, right. You can have several parameters on a system, right. If you look at a typical computer, the size of memory, that is a parameter, right. If you want to measure how many transactions per second can this database server have, then you say, oh, I am going to build a system, yes, but what is the memory, right. So memory could be 1 GB, 2 GB, 4 GB, that is a parameter, that is a controllable parameter, right. It is something that you have control over. Or the CPU, which is a single core, 2 core, 3 core, 4 core, whatever it is, that is also a parameter. That is a number of cores on the system is a parameter and so on. So here again we have two types of parameters, right. So these are the varied entities, right. So something that defines a system, right. A system is several subcomponents, in each of the subcomponents you are defining in terms of these parameters. Okay. So the two types of parameters you can classify them as system parameters right. So for example the number of CPUs or the number of cores, main memory size. Okay. So this is from the system perspective, these are all the parts of the system, right. Or if it is a switch, then you say the switch is operating at so many links and so much of backplane capacity, and this is the per link through bandwidth that is available, right. So that is all definition of what the system is. Okay. Then there is another type of parameter. What can that be? One defines the system, one defines the
environment.
Then the user, right? The usage environment. So the user of the system is the next one, right? So that is your workload. So what is these also you would vary. Right? So you would try whether my system works for 10,000 transactions per second, what is the response time, or 100,000 transactions per second, what is the response time. So that is what is being offered to the system, that the workload that the system processes, right. You can vary that too, number of transactions or number of short transactions, number of long transactions, right. Or number of users, if it in the case of if it's let's say medium access protocol you are trying to evaluate, right, aloha, either 10 users per system or 50 users per system, that is actually system level parameter. Or lambda, right, the traffic offered per user, the traffic generated per user, you may have 50 users, that is a system parameter, right. The system has 50 users, but each user generates certain amount of traffic, and that is variable, right. That is a workload that is offered by the user themselves. So this could be, right. So example, so there is a database or the number of packets, right, generated per system. So this is how you would, when you write your performance report, right, in the MTP or BTP, you would clearly say that these are my metrics, these are my parameters. In fact, in introduction section, introduction chapter, you normally have to say these things, right. These are the system parameters that I really considered important and so on. Okay. I haven't thought about that. Can it be? Workload is what is offered to the system. One is trying to characterize the system itself. So it, I'm not able to think of an example where it can be both. We will think about it. If you find something.
Parameter something like what we fix initially, and metrics is what the output we want.
So parameter is what you vary, right. So I want to study the system for 10 users, 50 users, 100 users, and I want to measure the average response time, right. Usually have this load, right. There is a notion of what is the load on the system, right, versus the delay on the delay that is measured. So delay is what is measured, and load is what you control. So one is a controlled, one is an uncontrolled thing. Yes.
So like response time, where will you put it? System parameter.
Response time is a metric. It's what you measure, right. So what is the offered load, and what is the, how does the system handle this load, and what is the output of it, right. So if you go to your mess, right, your hostel mess, then the system parameter is, I am not sure how your mess operates, hopefully they have several counters, right, and within each counter may be sub counters, right. If you have North Indian, South Indian, so on, they have a certain number of counters for each of those. That is your system parameter. The offered load is the number of students, right, that show up per hour, whatever it is, right, and that depends upon the total number of students on campus. This campus was designed for half this number of students, right. Then suddenly we have doubled the number of students. Then we have to go and scramble and increase the number of those counters, the tellers that we serve people, otherwise the lines are very long, right, which is probably happened in the hostel zone. We are trying to accommodate more students, but maybe not so the banks, where the number of tellers has been the same as it has been for, right, the last 20-30 years or so, because that is if you know that you have to add more people, but various reasons prevent you from adding, and you know that your system performance is going to vary. So there your number of tellers, number of counters is your system parameter, that is controllable. I can change it, right, and if I am not changing it, it's because of other reasons, right. But the delay is something that is simply measured. How long do you have to stand in line before you get your fees paid and so on. And this distinction is many times lost in many even research papers. Sometimes they don't really make that, but for this course, when I say metric, this is what I mean. When I say parameter, I mean it's a controllable parameter, right. So then this is little bit more exhaustive, right. You would like to see what are all the things that I can vary. I can vary the buffer size, right, in each router. On every link I can vary the buffer size, and I can also look at the cache, right. What is the cache size that I use on a particular CPU system if I am measuring a system. But then what we find out is we have to somehow have intuition or some background knowledge or simply prediction, right, or blind faith that all these parameters, I might have several levels, right. I might say that each parameter I can test for, say from 10 to 1 million I want to test the number of users or the size of sorting, right. If I am sorting array, I want to look at the size of number of users, number of data elements to sort, very small to very large. Then what happens is you keep on multiplying, right, for every possible number of users. I want to vary the main memory size and the CPU number of cores and the CPU number of CPU threads available, all those things, right. You slowly start getting into a combinatorial explosion. Then you start saying that, wait a minute, there are too many parameters to be considered, and some parameters might have no impact on your system at all, right. So what you want to do is you want to have some sort of estimate. See, if this is your metric, right, and this is your parameter. So you have to know which parameters are more important than the other ones, which ones will have significant impact compared to the other ones, and you would like to see if this is the right behavior after your experimentation, after the evaluation, that as this parameter value increases the metric increases like this, right. So here you find that there is a reasonably substantially sharp increase in with one particular parameter. So right, so we will say this is a parameter 1, and then there is another parameter that you vary, right. Let us say we can plot two different x axis, right, and two different y axis, and this is parameter number 2, right. Let us say this is main memory size and this is your cache size. So varying the cache size, your cache levels are so small that maybe it makes no difference, whereas going from memory to 1 to 2 to 4 GB will make a big difference, but going from 32 kilobytes to 64 kilobytes or 120 kilobytes has no real impact on your system performance, right. So that is something that you need to, now that you have listed all these possible variations, these things that you can control and vary, your next step is to identify the so we call them as factors. The most, because that is needed to control your experimentation space, otherwise we will end up with millions of experiments which some of which give you no meaningful information at all. There is no point in running against varying cache sizes and so on. So you should say, okay, which of these, even here, right, workload parameters too, I could have several parameters, and some parameters really maybe make no difference at all, right. So then you define the set of levels, for each factor. So level simply means the number of possible values that you want to try out, right. And here I mean these are many times continuous variables, right. So I could choose, for example, load, number of packets offered per second. I could go from 1 packet per second to a million packets per second, increments of 1, 2, 3, 4 and so on, and so that, right, it really makes no difference, no sense to have that many levels. So you say, okay, 3 levels, 4 levels, low load, medium load, high load, that is adequate, right. So those are the things that as part of your system performance evaluation you will decide. So for example, I will say that main memory, I will have 3 combinations, right, 1 GB, 4 GB, 16 GB. And this is initially a guess. Why not 8 GB, why not 12 GB? You could have done that, but you want to keep your search space small initially, so you say I am going to do 1, 4 and 16, okay. And then you would say load, right. Let us say we are talking about packets per second, so I will do 1000, 10,000 and 100,000 packets per second. So you have now pruned all the other parameters out of the picture, you only care about what is the memory, what is the number of packets offered per user, okay, and I only care about these 3 values. You usually try to go maybe 10 values or so, but depending on how much time is involved in each simulation run, right, or in each performance evaluation, even experiments also can take time. So this is again something that comes only by experience, right. You know that sometimes it is pointless, in the internet it is pointless to run 100k packets, right, 100k packet size. If you look at packet size as a parameter, right, 100,000 packets per second is okay, but if I say I add packet size also as a parameter, then you know that there is no point looking at very large packet sizes, because everything anyway gets broken down by the Ethernet layer to 1500 bytes or 9000 byte packets. So you would be some more reasonable saying I will do 512, 1024 and maybe 8192. and if you know more, saying there are only 2 possible packet lengths are there, 40 and 1500, you will simply try for those 2 packet lengths, right. So that is all domain knowledge that comes later on. Okay. So this is now you have spooned your search space to the set of specific parameters. Then of course right. Okay, then we choose whichever, right. We talked about this earlier on, math or simulation or experimental implementation. So in fact simulation, there is, we mostly talk about simulation in terms of discrete event simulation, right. You use the computer based simulation, but there is also analog simulation, which I remember doing a course on that several years ago, but I forget what it is all about. There is a book on that. I do not remember much from that book at all. Okay, so get the technique, and then you, now that you have the right factors, then define the workloads. Right. I could have done define workloads before selecting the technique, it really does not matter, but let us say that I have designed, I have actually, this is not only selecting but also implementing, right. I choose a simulation platform, I have implemented my algorithm, TCP algorithm in there, and now I am ready to evaluate it. So at that time I say what is the workload, right, what are the different types of combinations of workloads. Then right. Okay. So then design run experiments, right. So workload is defined, I can then run the experiments, and then what will be the 2 next steps?
Analyze your results.
Yeah, analyze, interpret data, right. And how many times you do not see that reports? You simply show a table and then say here is my table, that is all done. Right. I am supposed to figure out what this table is supposed to do, right. I have varied all these parameters, I see this nice graph, done, right. We see this in I asked you to do that in 604, right, assignments too, when I made you write those various combinations. This is, so analysis is more important, getting the data and then interpreting data. You should either things behave intuitively, increasing memory, reduce the latency, increase the number of transactions per second, therefore this is expected. If it does not happen, then what? Who is at fault? System's fault, your implementation's fault, right, or is unexpected behavior? You never know, right. You are expected to know when something goes out of order, right, that is not as that is something beyond what you thought would happen, right, that is not intuitively agreeable, then you have to explain. And many times you will find graphs that look like this, right. Load or whatever it is, right, it will go like this, right. This is some, say, delay, okay. Increasing load decreases the delay, and then it increases again, and then people are quite comfortable. Look, this is what I measured, right, whatever this is, oracle, it won't tell lies, this is it, just take it and go, right, understand that this is indeed the case. So if you are working for a company and the company says tell me, right, how the system behavior will increase the number of users online, right, you will say okay, increase the number of users, delay will go down, okay, because your client will not be very happy if you tell them that kind of solution, right. You will have to say okay, what went wrong, either you did your measurements of delay incorrectly, right. So the common measurement of delay, one of the reasons, so you have to go back and see how did I measure delay, right. Let us say that you are talking of packets coming to a router, right, and then you are measuring delay for those packets. Then you will have this policy of dropping packets, so you only count the delay of successful packets, okay. So what happens is when the for some reason, right, when the load is light, many packets got dropped because of errors, let us say simply link channel errors and so on, so a lot of packets got dropped, therefore only 2 packets got through, therefore delay is very high because, right, the 2 delays might be very large and therefore you ended up having large delays. Then somehow the system was better behaving when your load was different, right, some change in your parameter model, you did not notice that, and therefore large number of packets got selected for transmission, were successful, therefore delay goes down. Then when this is expected, right, as the load goes up, this delay is expected, therefore you say okay, as the load increases, delay is also increasing, but that is where you have to come in and figure out what is going on, right, simply presenting the graph and not explaining the graph, right. So one is to explain what is going on in the graph, and the second is to explain discrepancies in the graph, right. The other set of graph that you will sometimes see is like this, right, you will see those also, and it may not be that bad, but you will find those specific, very clear dips, ups and downs in the performance. So then you will have to say okay, now what is going on, right, either you are able to explain that or do more experimentation. So many times why something like this happens is, any guess? Sometimes you are not running the simulation for long enough and therefore your system is not reached steady state. So depending on the load, depending on the random variable, right, your seed for the random variable, you are therefore here the system was stable, here the system is still not yet steady state, therefore your delay values will kind of go up and down, so it is not a smooth curve. You will not always get these smooth, right, expectations, but you would still have to be able to, for load and delay, you know that there is got to be, right, that some expected behavior is there, and your job is to find out, right, what happened. Or it could be simply an implementation error, right, for some reason somewhere you are having some packets running out of memory, those packets are not getting created, but you are simply still proceeding without bailing out of the system. So that is, interpretation of data is really critical.
One more point I would like to say here is defining your set of levels of each factor and then defining your workload needs some guidelines definitely.
Yeah.
I cannot really go ahead and set some arbitrary values like say this.
Yes.
Say buffer size, if I have to talk about whether should I take as a 10 buffers or a 50 buffer or 100 buffers.
Yes.
Just to analyze the round.
So that will come from experts.
Is that the
in
experience?
That is, yeah. That will be more or less, or you simply blindly try out, right? You simply say I am going to fix all other system parameters constant. I will simply try varying this for say 10 different values. Then you find that these 3 are adequately representative. I need not go more than 3 such values, right? And that is simply, that will come from experience.
And the interleaving between these 2 levels.
Yes, that is also important. So sometimes what we find is that people will have plots that look like this, right? They will try to do a log scale, or they will say 0 to, right, 1 point, right? This will be in increments of 0.1 and so on, right? That is one kind of where you want to zoom in on a particular section of your graph, because you know that lots of things are going on in this 0 to 1.0, and then you have the same thing where you simply go from say 1.2 to 100, right, in orders of whatever 10 and so on, right. So that is again, if you want to know something more detailed, in more detail about a particular section of how the workload is affecting your system, you do the zooming in and then show that, right. That you should be able to figure out. Then okay, let us look at this 1.4.16 as an example, right. Let us see what happens there. Right. So I have only these 3 values. I thought those are good enough for my system, and I am measuring throughput, right. So this is throughput of the system. So this is transactions per second. So this will have increasing or decreasing, which is higher is better, lower is better, higher is better, right. So I would expect that this curve, okay. So from here, right, I see like this, and then I suddenly see like this, right. Then you find that right, is this necessarily a straight line between 4 and 16, right. If I put 8, right, where will I, where if I have 8 GB of memory, right, it will be, you should be curious to know what will be the transactions per second, right. Can I simply linearly interpolate and say because 4 is this and 6 is therefore 8 is this, you cannot really say, right. So you might want to say, okay, let me, right, see if 4 is here and 16 is there, right, in case I had with 4 gigabytes so many transactions, 16 also same number of transactions, then there is no need for further interpolation, because you say that 4 itself I am getting the same performance as 16. This happens with parallel processing, right. As you increase the number of CPUs, you find that beyond a point there is not much improvement in your performance, therefore you simply stabilize out. So you want to see at 4 and 16 there is a big jump, then you should definitely go back and do some more interpolation with real experiments, not simply predicting, because only have 2 values it is not enough to predict. So in this case you might want to, right, look at 8, and 8 might also be very closely up there, right. So you get a graph like that. So at 8 you are almost matching 16 gigabytes worth of performance. So you might tell the system provider or your manager that 8 GB is actually good enough for this kind of workload that we are trying to do. There is no need in going and buying 16 gigabytes of memory, right. But the manager might come in and say, wait, why even 8, right, what happens to 6, right. So where then your question is, okay, then I start looking backwards, all like binary search, right. So where between 4 and 8, right, do I find that the performance is maxing, and at that point I will draw my threshold, right. So you want to find out, say somewhere here, right, at 6 I am more or less maxing out. If you find it, that's when that only comes by experimentation, intuition, right. So you start off with intuition saying that these are probable values, then you find that I have to dig in further to get more details, right.
So sometimes one or more of these parameters can play, and
there is a combination
of them might prove to be the one which we have to experiment on. So how do we generally characterize something like that?
So what we will try to do that is, if it is, say, you will sometimes observe these plots where there are 2 parameters varying on the same graph, right. Either you do 3D graphs, which is very hard to look at, visually interpret. So what you try to do is you say, there is one more parameter, right. So this is parameter 1, this is parameter 2, right. So this is your second parameter, right, which is one value is, this is the first value, this is the second value, and so on, right. So then you look for combinations of at which load and which, right, what parameter value do I find the cutoff that I am looking for, right. So let us say that you want delay to be capped, right, somewhere here, that is the upper limit of delay that you want to tolerate, and you want to find out what should be the load, as well as if I am operating at X load, then I should be setting this other parameter to this corresponding value. So that will come in one of the chapters, this multifactorial experimental design, where 2 or 3 factors simultaneously impact the performance. So in the end what you also try to do is, other way what you will try to do is you fix one set of default values, right, then vary the system against those. So there is a lot of experimentation that has to be done, but once you narrow down to the most important parameters, then you can only play around with those 2 or 3 parameters. Okay. And then the last step is what we have been doing so far is present the results, right, and presenting results is also, right, an art by itself, and there too the default is put the values in Excel spits out one bar graph, put it out, right, and you do not worry about how it looks, does it really convey, right, what I am trying to show. None of those are clearly, right. Some cases bar graphs are good, some cases just line plots are good, sometimes pie charts are good. There are several variations, right, we'll talk about very briefly at the end, but one has to really experiment with those and then come out and say, also line types, color types, right, so many things are there that one can vary. It is the default thing is whatever Excel gives me. Excel really gives the lousiest stuff, okay, we can erase this. Excel really does not give you the best of graphs. There are several other tools. What did you guys use? R, right, okay, is R better than anything else? Okay, so that is sort of the, right, the template which one is expected to follow, right. As long as you have a template, just follow this, do this in a methodical manner, so that at the end your report, that whenever you are saying your system is better, right, you are saying that with confidence, you are saying that I have done all due diligence, I have followed all these steps, right, I have considered all the parameters and so on, and that that should happen. It just does not happen because of lack of time, right. Usually the 1 week before the Viva is due, the reports are written, in which time if you tell them to vary X number of parameters and draw all nice plots, they will say, okay, nothing doing, my Viva is due tomorrow. So do not let Viva be the reason for your the deadline for how you operate. Make sure that your report has, this is not just for your MTech BTech Viva, right, you go beyond this, you go to industry, they are going to ask you to do this, right. If you are to design a system, they will expect you to do some more rigorous performance evaluation, some more informed way in which you can tell which of these choices are better, right. It is always going to come up, whatever system you go to, whichever company that you go to. Even if you start your own company, you want to set up your own web service, and the first question is how many servers do I put, right, or what kind of service do I buy from, what kind of parameters, what kind of service parameters do they have, right, what is the metric, do they, which of these guys, if you have to choose cloud, now we have iCloud, right, coming into the competition. Why should I go to iCloud versus Amazon's cloud or some other cloud? How do we decide that? We can just get multiple accounts and then do our own testing for a while and then say yes, indeed this is better than the other. So that is it is more of I guess an engineering, right, set of steps. So now we will talk a little bit more about several of these things as we go along, right, and some of those things it's more of just telling you what should be done, and in every domain the way that you choose parameters, the way you choose your metrics is going to be different, right, that depends on what you are going to be implementing and what is more important than the other one. We were talking about chapter 2, right, the common mistakes in performance evaluation, how to avoid them. Yesterday we simply went over the list of what to or how to avoid, right. So we had a list of to-do list of setting state as to goals of the system and coming up with the right performance metrics, parameters and so on. There are a couple of items in that common mistakes list which I thought we should look at, right. So one of them there are, as I said, about 22 right, this is still from chapter 2, about 22 items that are there in that long list. Not all are well relevant to discuss now, you can still go through that at leisure later on, but a couple of things and we will see what we mean by that, right. So one is this is item number 6. It is unrepresentative workload, so which means choosing a workload that does not really depict the real expected behavior of the system, right, and under what conditions will the system be used, and so you are, let us say, choosing a load which does not capture your typical day to day expectations in terms of load of that system, okay. So one classic example, right, for that is let us say we are looking at a medium access control protocol, right, all of you remember MAC protocols from networks class. So we have two choices, right, one is random access based, other is time division based, right, or scheduling based. So for random access your classic example is CSMA, Aloha, right, you can even go to Aloha, CSMA, these are your classic random access protocols. And for scheduling based or TDM based protocols we have typical TDM, right. So if we were to compare the system of in terms of delay, let us look at the response time of the system. So I have a packet to send, and let us say there are 50 users in the system and I am comparing delay for these two systems, okay. So what kind of load should I choose? High load, low load, will it make a difference? What is the expected performance for these two protocols as I increase the load on the system? Load is simply, let us say I have 50 users, each user can generate certain number of packets per second, right, 0.1 packets per second or 50 packets per second, so that is your load. So load is your x axis, this is your factor, right, we talked about factors yesterday. So this is load, and the metric I am measuring is the average packet delay, the time it takes for a packet to be received at the receiving side. So once the sender sends the packet, how long does it take before the receiver gets it on the other side? If it is Aloha or slotted Aloha, right, what will be the expected behavior in terms of delay? Let us say each packet is 1 unit long, so 1 unit per packet, there are 50 users in the system, okay. When the load is very light, when each user is barely generating any, let us say 0.01 packets per second, right. So what will be the expected delay? Very less, okay, good. So how less? What is there a specific number you can think of? Load is very light, 0.001, what will be the expected delay? Just 1, right, you maximum 0.5, 1.5, if it is slotted Aloha, what do? You wait until the beginning of a slot comes, then you send the packet. So worst case you may have a delay of 0.5 before you get the channel access, and then you send the packet, that is simply 1 unit long, and there are no, assume that there are no errors in the system, right, no channel errors, the channel is perfect, therefore there is no channel error, only collisions lead to packets getting dropped. So if you measure it, let us say there is something like 1.5, right, that is the average starting initial lowest possible delay. So this is very low load and it goes on to very high load on this axis, okay. So for started aloha I will start off with 1.5, then as I increase the load what will happen to the delay, it will keep on increasing, right, okay, and then stabilize at some point, okay. Well, it will not actually stabilize, it will just keep going forever, because as collisions increase and you start retransmissions kick in, then you will find that you are always colliding, retransmitting, nobody ever gets through, therefore your delay just keeps on escalating, right. This is the access delay itself, okay. Now what about a case of TDM? So there are two delays in this system, right, one is the delay when you get to the top of the queue before you can actually get sent, the second is waiting time in the queue itself, right. So let us look at only the time, the final access time, how long should I wait before the top of the packet, the top of the queue packet gets selected for transmission. So what will that be in the case of TDM, what will be the average delay? So TDM is, there are 50, right, if you remember TDM definition, in a TDM based Mac if I have 50 users I will have 50 slots, right. And we have the standard slot 1, slot 2 and so on, right. Remember that every packet is 1 unit long, so therefore there are 50 slots, because there are 50 users I have to give every user 1 slot, this is your classical time division multiplexing, right. So this, and then this frame repeats perpetually, whether there is user has a packet or not, user always has a slot assigned to that user, right. So slot 1 is always for user 1, slot 2 is for user 2 and so on, that is the default definition of TDM. In this case what will be the delay once a packet gets to the head of the queue, average delay? Worst case it is 49, best case it is 0, so average would be n by 2, right. If I have n users, if there are n slots in a frame, so the average, what happens is, if let us say 50 is your slot and your packet got to the head of the queue, right, let us say just before 50th slot, then your waiting time is 0, almost negligible, right. Or the worst case your packet arrived to this queue just after your slot started or slot finished, in that case you have to wait for the entire, right, cycle. So if it arrives just before, your slot waiting time is almost 0, if it just arrives just after, you have 50 unit of waiting, therefore the average you will see is 25, right. This is the guess, this is where your performance evaluation starts, right. The first step is to look at some sort of mathematical intuition as to what should be the performance of the system, so that is where this is your classic. Then what do you do? So you would find that the delay is 25, right, this is average delay, per user, right, depending on when the packet comes to the queue, you will find that sometimes it comes early, sometimes it comes late, and therefore there is this little bit of, right, variation in the system. So this is our guess, we can verify this by simulation, right, by simple mathematical computation we are saying that it should be about 25. So now what will you find, is this going to vary with the load in the system, right, because it is independent of the number of users, whether 50 users or 100 users are there, you always have your slot, only thing is you have to wait for your slot to arrive. Therefore I would say that in terms of the waiting time, right, or the channel access delay, it is more or less constant. If I add queuing, then it will become dependent on the queue size, then it will vary with load, but this is excluding queuing. If I add queues, this will also become like this, it will sort of go like this at some point in time. This I am not looking at the queuing, just the time taken. So the bottom line is, at light loads, right, the delay of started aloha will be less and the delay of TDM will be more. So if you want to say that I have got a better algorithm, the best way to do that is not even bother showing, right, your load stops there somewhere here, right, you say that I have simulated for from here to here, my system is always better than TDM, right, therefore stop at that point and then close this, then finish your thesis saying I am done, right, my algorithm is definitely better than this existing algorithm, assume that only TDM was known, there was no aloha, right, you will propose this and say I am better. So that is what is called as an unrepresentative workload, your workload does not really capture the fact that you could also be operating in higher loads, right, but maybe in a system there are cases where this is actually adequate, where your number of users generating traffic is fairly low, in which case actually aloha is better, right, but that is something that you should know and predict. So when you give your report to the system or back to your whoever wants to know about this particular system, you should look at loads that consider the entire spectrum, right. So in fact Aloha was one of the early protocols, right. This was designed for satellite access, and they knew that this is not the best protocol, right. We will see later on time permitting 18%, 36% maximum throughput in Aloha started Aloha, right. We can actually derive those things, but they knew that the load on the system is very light. For that lightly loaded system, Aloha is better. But if you are going to say I am doing a comprehensive evaluation of two systems, you should look at the entire all the possible combinations of workload. Okay, so that is one classic example. Then the second is let's see, yeah, overlooking important parameters, all those things we can look at later. Yeah. Then we will look at 16, right. This is with respect to outliers in the data. Right, improper treatment of outliers. So outliers are when I am taking a sample, right, of some metric over different load values and so on, you suddenly find that there are some numbers which do not really fit the trend, right. You know some expected trend is there as load increases, delay increases and so on, but sometimes there is these ups and downs in the graph. We saw that briefly yesterday, right. So outlier could be, so again the trend is normally like this, it goes up, but suddenly it comes down and it goes up, right. There is one value where this expected trend is broken, right, and after that it again starts catching up. So this is an outlier, right, with respect to the rest of the data. So it is breaking the trend that we expect to see, and the normal thing is go back and see something wrong with the code, right, something wrong with the load for this particular value of load value, why is the system behaving so. So you are expected to go back and check your because theory might show you that this actually is a smooth curve, right, but in simulation you are finding that there is some problem, even experimentation also there is some particular problem. So this is not only simulation, right, you could be running experiments on a particular system, you are comparing two sorting algorithms, right, algorithm A, algorithm B, and you find that algorithm A is generally giving you this consistently increasing values, and when you increase the size of your list, the list to be sorted, and therefore suddenly you find that there is this one jump, right, one jump here, right, because what should be what happened is let us say that these are the different values, right. So where is the outlier here, right, I expected the value to be somewhat here and the value is gone there, then you can, the best thing to do is ignore it, right, and just okay there is this one outlier, I do not know what happened. The other is to find out if you can actually replicate that. That is sometimes hard with experimentation. You run the same sorting algorithm again, saying okay let me see if I get the same right set of results, the same trend show up again. Second time if it does not show, then you know that okay there was some transient behavior in the system, right. Just when you are running this particular data set, your something started downloading, right, at 10 o'clock it got turned on, started downloading, your CPU got busy, therefore your searching time, right, or sorting time for that particular data set was bad. So you try to repeat the experiment first and then see if you can same trend is noticeable, and if it does not then great, otherwise you have to go back and look at the code, right. There is something wrong in your code when a particular value of that load value is set, right. So we should ignore or should avoid the tendency is to simply do not plot that value at all, right, plot this, plot that, right, and then you are done. But that does happen, right, just delete that value from your file and keep moving along. So you have to go back and look at outliers. Some of it sounds like ethics class, but anyway, but these are things that do occur, but you should have the intuition as to why your system behaves that way. Either explain your particular behavior, right, or do not explain at all. So another case where you would see this is, right, if I look at again Aloha or starter Aloha as the example, and I vary that load versus, so this is increased offered load, right, increasing offered load to the system, and here I am measuring the throughput. Throughput is in terms of number of packets per second that are being generated. So in Aloha if I have only one packet, maximum I can send one packet per slot, right. So this is throughput in terms of number of packets per slot. Okay. So throughput will be proportional to load. If I offer let us say 0.5 packets per slot, that is the total offered load, then the number of packets sent per slot is also 0.5 per slot, right. So at some point you will, till some point your load and the measured throughput should match. So you will see some sort of behavior like this, right. It goes up like this, it goes up like this. It kind of more or less linearly keeps increasing with the load offered to the system, and then you find that now you are suddenly some outlier beginnings, you find that it starts dipping like this, right. That is expected behavior in Aloha, yes or no? Why? That is when your 36% limit comes, right. So if you did not know that there is this, somebody else has told you about 36%, or if you did not think that, you know what, beyond some point collisions will happen so much that you cannot really send any more packets, right. So this is starting to show the beginning of some sort of outlier. So you can just say that, well, I will stop my simulations at this point, right. There is something weird going on there, maybe my simulation is incorrect or my model is incorrect, right. So here is where you should have intuition about why the system is behaving in this particular way, right? And in the case of Aloha it is very easy to figure out the intuition, but in some cases it is not, right? When you go to more complex systems, a lot of subsystems are involved, then it is very hard to predict as to why, right, some of these things are happening, some of these outliers are occurring. So you do your best to explain, and if not, just state in your thesis report that, you know, there is this weird outlier, I could not explain this, and just leave it at that, right, than just try to hide that if it is a repetitively occurring outlier, right. So that is improper treatment of outliers, that is another common mistake that should be avoided. Then one more example is improper presentation of results, right, or even analysis of results. Oh, it is not 17 actually, according to the book number it is 20. So your first chapter, right, there is this comparison of two different systems. So I am, let us say, measuring throughput of two different router implementations or some protocol implementation, and okay, so I am measuring throughput. There are two systems A and B, and I have two workloads, workload 1, workload 2. Okay, throughput in some unit, does not matter what the unit is. Okay, now there are these two units. Okay, 20, 10, 10, 20. Right. So in one workload, system 1 gave 20 throughput, 20 units of throughput, whereas system B gave 10 units of throughput, and reversed in the other case. So which of these two, you are supposed to compare these two systems, right? Only these two values are there. So which is better? This is again what you will see sometimes in thesis, right? I have done two values, I am done. I have compared two different systems. Okay. So which is better?
In this case, we will say that system A is better when the workload is WL2, when the workload is more, say, then system A is better, when the workload is less, then system B is better.
Okay, so this could be, say, two different workloads, and therefore, so this could be high load, low load. Okay, so in that case you might come out like in the case of TDM where we said that one is better, but let us say that this is two different random seeds, right. When we generate traffic in a system, there is some randomization in the generation. So I could always, you have to actually do multiple random seeds, initialize the random seed differently each time. I get, you know, so that the same lambda or the number of requests per second is arriving, but the way in which they arrive is there is some randomness in that, right. Therefore this leads to these two different values. So let us assume that same load, workload, but right, differences in the way the traffic is generated. In that case, what happens? Can you conclusively say that one is better than the other? If I simply, I will say mean, right, I will compute the mean throughput. So the average throughput is 15. You find that this is not satisfactory and you want to finish up writing your report, right. So you need to find a constructive way of showing that system A is yours and you want to show the system A is actually better than system B. So how can we play around with this in terms to see if I can make system A better than system B? Okay, now let us say that you are running out of time, right? It is due tonight, no time to take more points, either you cook up points or you have to use these 2 points, right?
Workload 2.
So one is to simply show only workload, but your advisor is not happy, say no, 2 workloads are needed, one is I simply can't accept with just one workload, right? Okay, that is when you start playing so called ratio games, right? So let us say I compute, instead of throughput I say ratio of throughput of system A to system B, right? That is my metric now. I have changed my metric from simply throughput to ratio of throughput of these 2 systems, right? So this is ratio defined as throughput A by throughput B, right? I can do that. Now this actually course supposed to teach you good principle practices in performance evaluation, but this is not does not fall in that category, okay? So if I do that ratio, now what will happen? So this is 2, right? This is 1, actually this average should come here, not under here, so that is 2 1, and this is 0.5 and 1, right? Okay. So both systems, system B is compared to system B, therefore ratio is 1, system A is compared to system B, therefore ratio is 2 and 0.5, right? Then I compute I say okay, my metric is this ratio, I will compute the average improvement of system A with respect to system B, right? So I compute the average here, average of 2 and 0.5 is 1.25, average is 1, right? Therefore system A is better than system B. That's just, either you can call this analysis or presentation, whatever it is, but right, this is the way you twist the results to show that this is a better way to do that, but this is not what one should do, right? But when you probably might see this in papers, and then you might say okay, now this is not correct, right? Not only papers, even when you go to companies, right, you might be asked to compare 2 different systems, and when you run out of time and your boss says the report is due yesterday, then you say okay fine, I will show you that this system is actually better, right? Because you have to compare your implementation to some other competitor's implementation, and then you have to somehow make the boss happy for that day that your implementation is actually better. So you can you can use all sorts of tricks to come up with different metrics. So that is an example of this improper analysis or presentation of results. Okay. So the list goes on, right, and you can look at that later on, right? So this is our conclusion of chapter 2.